A quick recapitulation, we have talked about derivations, we have given the definitions, and then we have said what is called an art derivation, right? And then these were some simple observations. Uh, this proposition is very important, which said that if you have the polynomial ring in n variables, then there exists derivations such that the variables you can send them to these values, in the sense that di of xj equal to this Kronecker delta ij, and these derivations are determined uniquely. And moreover, this is a very, very important statement. As you can see, that this is a free R dash module with basis d1, d2, dn. Okay, so this we have proved, and we would like to have a similar kind of statement for regular local rings. That's the idea. In fact, there we will see that it's an if and only if conditions. If we assume some good properties, we will come to that today. Okay, so that's the main purpose behind this section. Okay, so we have discussed this in detail, and in the process we have in fact introduced these names. If you remember this, we called them the partial derivatives, these di's, the ones which are taking this xi's to di, taking xi to 1 and other ones to 0, and this is a more common notation for that. Okay, and therefore we can say that every R derivation of this polynomial ring over R in n variables, that has a unique expression of this form, where bi's are polynomials. Okay, in fact these bi's you can easily evaluate them to be dxi's. So that's the idea, that this is what about the derivations. And then if you remember, I just quickly introduced the notion of differentials. We need to talk about the module of scalar differentials, because that would give us the criteria, the differential criteria for regular local rings. Okay, so let us go through the defining property come this proposition, and then we will get into the details. Okay, so R is a commutative ring with identity, R dash is a commutative R algebra, and then we said that this pair, this omega d of R dash module omega and an R derivation d. So R derivation d is from R dash to omega. Okay, and that is unique up to a unique isomorphism with the following universal property. Now this universal property, that is that what we will be using all the way. So given a pair of R dash module m and an R derivation d from R dash to m, there exists a unique R dash homomorphism phi from omega to m, such that this diagram is commutative. So this is the universal property, that if you have an R derivation here for an R dash module m, okay, and this is the derivation that has come with omega. Okay, now this object is what it is going to do is that this derivation would again it would factor through this unique R dash linear map from omega to m. So this is the universal property for the module omega with the derivation d. Okay. Okay, now this is unique up to unique isomorphism, etc. That is a kind of a standard technique which we do for proving this uniqueness using universal property. So that is not something very new, but the existence of this omega has to be talked about, and that that can be done in a couple of ways. But I'll do it in the way which I believe is very important, and it has its own merits. So I will be, let me give you the caveat that in the lectures, probably there will be certain parts where you will keep seeing these green lines with E stroke T, etc., or some statements which we have just mentioned. Okay, but the whole idea is that otherwise it would be very, very difficult to cover the entire thing. What I intend to do is that, but the story is complete, that you will understand. What I intend to do it eventually, when this notes gets finalized, then I will add those details in the correct places. Okay, so that it will be kind of self-contained. So let me try to explain it to you. So what I'm talking about now is the construction of this omega. Okay, so your R dash is R algebra. Now you take this map mu. If you remember, we have already talked about the tensor product of algebras, right? When we were talking about tensor product in maybe second, third, fourth lectures, then we have actually in detail talked about these maps. How do they exist? What kind of universal property would ensure the existence of these maps and their properties and so on and so forth. So here we are now in a position to use them. So mu is the R linear map given by mu of B tensor C equal to BC for BC in R dash, okay? Then you can understand this is the kernel, of course. So mu is a ring homomorphism, and the ideal I, the kernel of that, is actually generated by this. As you can see, I have put it under green line, but this is very easy to verify. This you can verify very easily. Now this will be actually useful because we will be using I square, and you will see in a minute, yeah, you can see it right here, that my definition of omega is going to be I mod I square, okay? So this module, I claim, that satisfies that universal property which I have just now talked about, that if you have an R derivation, then that factors through a unique R dash linear homomorphism from this omega to any other R dash module M. So therefore, you can understand what is going to be done, that I'll be defining a map and from I, and then I will be showing that I square is actually getting vanished under that map, and that would give me a map, and then the other things would follow. Okay. Okay. So as I was saying, that these generators for I would be useful because we need to know I square a little more in detail. Okay. Otherwise, it will be difficult for us to show that whatever map we define, then that map is actually killing I square, right? Okay. So we can make this R dash tensor R dash over R into an R dash module via the ring homomorphism. These things you have seen before. Now this induces the R dash module structure on omega. Okay, so omega by definition is I mod I square. Okay, now we have to define this D. If you remember, take a quick look, or maybe once again, perhaps it makes sense to, maybe I just take you there. Yeah, don't forget this, keep this picture alive, that you have a D, you have a R derivation, given any R dash module, if you have an R derivation, this omega comes with a D. This D is what we are trying to define now. So, and we will be proving the universal property in the sense that given any D, which is a R derivation, there's an R dash linear map from here to here. Okay, such that the diagram is commutative. Okay, so we are trying to define that D now. Define D from R dash to omega by dB equal to eta of 1 tensor B minus beta tensor 1. Basically, eta is nothing but just the canonical surjection from I to I mod square, I mod I square. But just this, instead of writing the bar, this map has been used because this will be a little more, the expression would involve eta quite a lot. So that is why this notation has been used. So this is the image of this element in I mod I square, basically. Okay, so if you define this, then once again you can see an I stroke T that D is an R derivation. So this checking is also not difficult. You can show that it's a derivation, and in fact it's an R derivation. You remember what is R derivation? That means, so you have the R linearity. Okay. Now what do you have to show? You have to show the universal property. Okay. So now some quick checkings, and it would follow from the description of I. Description of I means this. This is I as we have claimed it to be. It follows from the description of I that omega is generated as an R dash module by this. Okay. So this is kind of obvious because you can see how you have defined D. Okay. dB is basically the image of this element, isn't it? So therefore, the image of these elements means you all take the generators of I and then push them down to I mod I square. Okay, now we show that this satisfies the required universal property. So you start with an R derivation from R dash to M, and then define phi from R dash tensor R dash over R to M to be the R linear map given by this. So you just basically check that this map is in fact R dash linear.
Sir, can we see two slides at a time?
Prefer that? Yeah, sure. Okay. So, so we are now trying to prove the universal property. So start with an R derivation, okay, and you define your phi to be this, and checking that it's a R dash linear And also it follows from the description of I that I square is generated as an R module by this. I was telling you, right? I mean, eventually I would require I square in detail, because I am going to show that I square is getting vanished by this map phi. When you restrict phi to I, and then if you have take elements of this form, then you will be able to see that it actually becomes 0. Okay. Yeah. Okay, so you use Leibniz condition because D is a derivation, and then you find that phi of I square is equal to 0. And hence because you remember phi actually, yeah, I need not go there. Yeah, if you remember that phi is actually using D, which it has to, okay? And then it follows this. So these are small details, please check. I mean, because these are not difficult at all, and take these as kind of small checkings. These are not the hard parts, but there are certain results which we will be just using as it is, okay? Okay, so hence the restriction of phi to I factors via omega. Omega is I mod I square. So let us denote this factorization again by phi, and then you can check that this commutativity of the diagram actually happens. And the uniqueness of phi actually follows from the fact that omega is generated by this set. Okay, and the uniqueness of this pair follows from the universal property. That is the standard application of the universal property. So you see, this is your module of Keller differentials, as we call it. So this is usually the notation omega r dash over r, where r dash is an R algebra. And this is what is called the module of Keller differentials of r dash over r. Now the question is that, so this module of Keller differentials, how is it going to help us understand the regularity conditions? Okay, so this is now what we aim to do. Okay, so maybe I just keep this open for the time being, this one open for the time being, and move on to the next one. Okay, so a few names, the derivation from r dash to omega r dash over r, this is what we have defined, if you remember, is called the canonical or universal derivation. Now comes a very important corollary, because this will be extremely useful when we finally talk about the criteria, that der r dash m over r is isomorphic to this module, that r dash linear maps from omega r dash over r to m as r dash module via the map given by, if you take a phi from here, okay, then phi is getting mapped to, you just compose it with the universal derivation, then that will actually give you an isomorphism. In particular, this is the r dash dual of omega r dash over r. So as you can see, I have just safely kept it E stroke T, because you can understand sort of, can somebody suggest how to prove this? I have not talked about it much, but can you have a look, and can someone suggest how to prove this? Does it follow from the universal property? And then this is the part which we will be using, and a very important observation. In particular, if you take m to be r dash, then you know this is how we write it, right? Der r dash r. So, or the r derivations on r dash. That's how we call it. That is the r dash dual of the module of Keller differentials, omega r dash over r. Okay. Is there, okay, so think about it. I mean, we will come back to it. It's not difficult at all. It's just the universal property, basically. Now, and again, a very important observation. This will also be extremely useful while we get into the characterization, that omega r dash over r is generated as an r dash module by this set. By this set means, by this set, you understand what I mean, that this is the universal derivation applied on all the elements of r dash, and then the images of all the elements of r dash under the universal derivation. Okay, so this proof actually you can, one way of talking about it is using the construction itself, because we have already mentioned, right, what is omega generated by. But you can also use the universal property to show this. So I thought that let me just talk about it quickly, because you have already seen one such thing when we were talking about flatness and using tensor products extensively. So if you are just using the universal property, then it would be something like this. So you just call omega dash to be the submodule generated by this set, okay, by this set. And then what you want to show is that if you call J is the inclusion map from omega dash to omega, you want to show that this actually is an isomorphism, right? The inclusion map is an isomorphism. If you remember, in my second or third lecture, we have once seen such a situation. So it's something similar. So that's why I thought that good to revisit such a thing. Then D, so basically you will be using the universal property once again, that D gives rise to an art derivation from r dash to omega dash such that this happens. So by the universal property, there exists an r dash homomorphism from omega to omega dash such that this you have d dash equal to phi d. Just keep your eyes here on this picture and you will understand. And then you get this, okay? And then you have the uniqueness and universal property. Uniqueness of universal property tells you that your J phi has to be, this J phi has to be the identity, and that proves that J is an isomorphism. So omega dash is equal to omega. So so this is something which will be useful for us when we are into the differential criteria. Okay, so just keep these two things in mind, but I will again open this page for you. Maybe let me just keep this page open right here. Yeah. Okay, now time to come to the criteria itself. So what we are trying to do is we are trying to prove. So let me show you the theorem first, and you will understand. Of course, there's a bit of work to be done before we actually prove this, but let me at least show you so that you understand the context. Yeah, so this is going to be the main theorem that we are trying to address to. So if R dash is the localization of an affine algebra over an algebraically closed field of characteristic 0 at a maximal ideal, then R dash is a regular local ring if and only if the module of Kähler differentials of R dash over K. Okay, K is this base field, is a free R dash module. Sorry, this should be R dash module. Yeah, okay. So is a free R dash module of rank dimension R dash. So this is what we are trying to show, that the module of Kähler differentials is free of the rank dimension R dash, provided R dash is the localization of an affine algebra over an algebraically closed field of characteristic 0. So this is the differential criteria that I am talking about. So we are going to prove this. So you can understand that we have a particular situation where our algebra is not going to be an arbitrary one anymore. It's going to be an affine algebra. So we need to sort of see the dir and the omega a little more closely in the context of the affine algebra. So that means finitely generated algebras over a field. So that's what we will be doing now. Okay. Yeah. So this is what I was talking about. These are two technical lemmas, that how does the omega behave under localization. Okay, so when you have a ring of fractions, if you take S is a multiplicatively closed subset of R dash as it is an R algebra, and S is a multiplicatively closed set, then if D from S inverse R dash to S inverse omega R dash over R if this is the derivation extending this derivation, okay, then you have that the module of Kähler differentials for this extension S inverse R dash over R is basically you take the localization of the module of Keller differentials of R dash over R with respect to S, and that's it. That pair actually they match. So you can understand that you are going to use the universal property to prove this, but I deliberately have avoided it for the time being. So I have put it on the purple color, which means that it will be added eventually. Okay. And another proposition, this also will be useful, kind of technical lemma, but very important, that if you have a multiplicatively closed subset of R dash, if E is a subset of R dash generating R dash as an R algebra, then this omega S inverse R dash over R. So we are now talking about the module of Keller differentials under the extension S inverse R dash over R. That's it. Okay. Then this is actually as an S inverse R dash module, it's generated by this set D of E dash, where D is this universal derivation and E dash is the canonical image of E in S inverse R dash. In particular, if R dash is a finitely generated R algebra, then this is also finitely generated as an S inverse R dash module. Now, this is what we really need, because if you have a finitely generated R algebra, then you have a finitely generated module for this. Okay, this is very, very important. The module of Keller differentials is a finitely generated module over this extended this algebra S inverse R dash. Okay, so these proofs are not difficult, but I have just carefully avoided them for the time being. Okay. Okay, so now comes, I was telling you, right, we are gradually situating ourselves in the context of polynomial algebra and affine algebras, because the differential criteria is on affine algebras, which we are going to prove. So if you have the polynomial ring in n variables over R, then omega R dash over R is a free R module of rank n with basis dx1 dxn, where d is this universal derivation. So we have, what have we proved before? Our previous result was this, that if you have a polynomial ring, then you have some particular derivations d1, d2, dn, okay, with this property, and you have proved that DIRD is a free R dash module with basis d1, d2, dn, and now you are showing that the module of Keller differentials is also a free R module. Only difference is that here it is, you remember what is D? D is the universal derivation. That means this is D. This is D. Okay. So this is, if you just take, this is the polynomial algebra. So just take the variables, take their images. They are the differentials. These are called the differentials. So these dx1, dxn, they actually generate this as a free R module of rank n. Okay, so this is what we are going to prove first, and then gradually get into the differential criteria. Okay, so start with free R dash module of rank n. Oops, just a minute, please. Yeah, sorry. Okay, so f is the free R dash module of rank n with basis e1, e2, en, and let d from R dash to f be the R derivation given by dxi equal to ei for every I. You know that we can do that, right? I mean, if you have the polynomial algebra, then if you have some pre-assigned elements out here, then you can just assign your d, you can define your d in such a way that you just assign these as the values for these variables, and that's it. Then you will have this thing, the derivation. So we shall show that this pair f comma d satisfies the universal property required for your module of Keller differentials. You wanted to show what? You wanted to show that this is a free R dash module of rank n. So you have a free R dash module of rank n, and if you can show that this also satisfies the required universal property, then uniqueness criteria would do the job. Okay. Okay, so take any R derivation. So again and again, it's the use of the universal property. Take any R derivation from R dash to M, where M is an R dash module, and define an R dash homomorphism phi from F to M by phi of ei equal to delta xi. That's the most obvious thing to do for every I. And therefore, you have this equality. Okay. Now delta and phi d are two R derivations from R dash to M, right? If you remember, when we just introduced derivations, we said that these are some easy observations, okay? So which agree on each xi. But if you know that they agree on each xi, then again, by that previous proposition where we showed that the derivation module is free, we can say that since they are taking the same value on these variables, okay, so therefore they agree, and then uniqueness of phi results from the fact that E1, E2, En generates self. Fine. Okay, so if that is the case, then yeah, I'll come to that in a little later. So therefore, you basically your proof was done. Only thing is that the language was not ready. So now you have the language also, in the sense that the when you prove that when you prove this statement, let me keep this open. When you prove this statement that you can actually send them if you remember, this lemma was extremely important for proving this statement, that if you have a polynomial ring in the variable x, and if you have a derivation, then given any m in M, d extends uniquely to a derivation this, such that dmx equal to m. Moreover, if d is an R derivation, then so is dm, etc., etc. This is how we use this lemma to prove our main proposition, right? So in defining these DI, so you assign these, you fix the elements in the target, and then you can define the derivation in a unique way. Okay, so that's it. So the ground was prepared, and now you are just only bringing this chap into action, and then you have the universal property to just worry about. That's it. And therefore you have proved that this module of Keller differentials is free. So you see the regular situation for the first time here, right? So now you are going to going to talk about a similar statement in the context of regularity for affine algebras in general. Okay, so you are going to push from polynomial algebras to its quotients. But in order to do that, some more work is required. So let us see what we have to do. Yeah. Okay, so let me now keep this open. Now I believe the universal property has sort of, you will be able to recall this very quickly. So if you have the rational function field in n variables, then your module of Keller differentials, that is big K and this is small k. I hope you understand this with this curve is the small k and this flat one is the big K. So the module of Keller differentials over capital K is the dimension is n. More precisely, if d is the universal derivation for this extension k over k, then dx1 dxn is a k basis of omega k over k. Okay, so here basically what you are doing is you are just using that, you remember we just wrote down those bunch of these ones basically. These ones, right? So how does it behave when you have a localized situation? So you just take the S to be k x1, x2, xn, the polynomial ring minus 0, and then localizing it with respect to that, and you go to the field of fractions. So this is the rational function field, and therefore you just apply it there and you get your result. But all these are very, very important, and you have a corollary that if you have a finitely generated and separably generated field extension, then this dimension, so not just, so you have an extended extension. So here it was a very particular situation. If you have any finitely generated and separately generated extension, then also you can actually write what the dimension is. This is going to be the transcendence degree of L over K, and consequently you can prove that this dimension is also transcendence degree. Once again, I have just skipped this proof for the time being. This is not difficult, but I've just skipped it because I don't directly need it at the moment. So that is the reason I have just sort of remained silent on the proof, but I'll add it eventually. Okay. Okay. Fair enough. So now I have quite a few observations, and especially this one, which I would like to keep open here. Yeah. So that this statement about the dual thing, okay. And now we can gradually move on to the differential criteria for derivative. Yeah, just give me a minute. Okay. Okay. So you will see that we are introducing a new thing, but you will understand that this kind of obvious. So you have a Noetherian local ring. We are going to define what is a coefficient field of R, that is a subfield, the small k of R, such that the natural map from K to R mod M, you can understand K to R mod M, obviously, is an isomorphism. Okay. So in this case, we identify this K with the residue field R mod M, okay, via this isomorphism. Moreover, given A in R, now this is very, very important. Given A in R, so if you look at A bar here, then it would have a unique pre-image out here. So there is a unique A naught in K such that A minus A naught belongs to M, and we call A naught the constant part of A. Okay. Now this is, uh, uh, can you think of a situation where you have to talk about this coefficient field, because anyway residue field was there, because I have a local ring and naturally there is the residue field, right, R mod M. So again I am talking about a coefficient field, and that is isomorphic to the residue field sitting inside the ring. Have you seen such a situation? Can somebody give me a hint? You will see it in the next slide, but before that, no?
In affine algebras.
Sorry again.
In affine algebras.
In affine algebras, absolutely. So in fact, if you remember when I was showing you this this theorem, right? That you have a characteristic zero algebraically closed field, and then you have an affine algebra, and then you are localizing it, and therefore you are getting a local ring. So you have this base field, right? You have this base field. So this is the field we are talking about. Okay. So you can think that it is your residue field, but then you will see that this explicit observation will be useful eventually. Okay, good. So the first lemma, that if you have a Noetherian local ring with the coefficient field k, then the k vector space, this dir k r, that means dir k r, is dual to the k vector space M mod M square. More precisely, there exists a natural k isomorphism for dir r k k to home k, this, okay, obtained by the map that d going to d restricted to M. Okay. So we are basically, you can understand that this is something similar we have already said here. So we are now in a particular situation that we have a Noetherian local ring, and we are particularly interested in this very module. You know what it is. Okay. So we are now going to show that this particular map itself is a natural K isomorphism. Okay, so proving that is again kind of mostly routine. That if d from R to K is a derivative, please don't forget your coefficient field. I am saying that coefficient field K. Okay, but you can understand that you have the isomorphism with R mod M. But we are saying it explicitly because you have already seen this, that you will have to talk about affine algebra over some other field. So that is why we are bringing that into picture. Okay. So if d from R to K is a derivation, then dm square is contained in mk, and that is 0. Okay, because you have the derivations over k, etc. So these things should follow. And then the map phi therefore makes sense. So map phi therefore makes sense means what? When you are restricting D to M, your question is whether you have a k linear map from here to here, right? So since D is vanishing on M square, therefore you do have, it gives rise to a k linear map. And now if you want to show that it's injective and surjective. So if you have D in the kernel, so a derivation, what derivation? It's a k derivation from R to K. And you want to show that this restriction, when you send it to this map, okay, if you assume that this map is 0, then you have to show that this is the 0 derivation, right? That's what you are trying to show now. Okay, so assuming this, now let A belong to R and A0 be the constant part of A. Please don't forget that this is what we have called the constant part. Okay, for any A here, if you A bar would have a fixed unique pre-image, and then you call that A0, and then you say that A minus A0 belongs to M. So therefore, here, if you start with an A, and if you have A0 to be the fixed, this constant part, then A minus A0 is in M. Okay, but then it's in M, so therefore you have this vanishing, and this is dA because your A0 is the fixed constant part in K. So therefore you have dA, D is 0, therefore phi is injective. So I told you, right, just follow the kind of the conditions given, that what kind of derivation it is linearity with respect to what and so on, and then the proof follows. And now you are going to prove the surjectivity of phi. Remember, this is your phi. Maybe I just now move on to this slide. Here we are trying to prove this. So if you have a map here, then define your phi from, sorry, not phi. I wanted to define D. I meant D. Okay, so define from the derivation D from R to K as follows, that if you take an A in R and then A0 is the constant part, then A minus A0 belongs to M. So define F to be, you just take A minus A0 bar, that is the natural image of A minus A0 in M mod M square, and apply F on that. Okay, so since A0 is determined uniquely by A, D is well defined. So that is all right. And also it follows that D is K linear. These are some simple verifications. And to verify that it is a derivation, so now what you want to do is you just start with two elements. You have to check that it has the Leibniz condition. So you just take two elements A and A dash, and suppose these are the constant parts A0 and A0 dash. Okay, so and you just write it in this way. Therefore, since these are in M, so therefore this whole thing is in M, which shows that this A minus, oops, sorry, this is, yeah, it's fine. So A dash is the, actually it should be A0 dash. I'll make the correction. This is A0 dash is the constant part of A dash. And therefore, if you apply now, you just write D of A dash, you are proving the Leibniz condition. Then this is F of this by your definition. And you rewrite it, this part has been rewritten like this, and therefore you are left with just this A dA because of linearity, etc., and it follows that D is a K derivation, and therefore you have the surjectivity of phi. Okay, so so therefore, I mean, these are observations. What are you basically doing? You are relating your dir with the module of Keller differentials. That's what you are doing. And what you are saying is that you take the dual and then you get your derivations, right? So now that is what is going to be of much use for proving this theorem. Now let me prove this theorem. So this is going to be our very, very important result. Okay, so this is the criteria. This is the criteria for a regular local ring, what is called the differential criteria. So if you have a localization of an affine algebra over an algebraically closed field of characteristics 0 at a maximal ideal, then R dash is a regular local ring if and only if the module of Keller differentials, omega of R dash over K is a free R dash module of rank dimension R dash. So let us begin. So R dash is given to be R localized at P, where R is a finitely generated. Well, this there's just a everything we are talking about is commutative here, so no problem. R is a finitely generated K algebra, and P is a maximal ideal. Let M be the maximal ideal of R dash. Okay, so P is a maximal ideal because we have localized at a maximal ideal. Now let M be a maximal ideal. M be the maximal ideal of R dash. So therefore, you know, this R dash mod M is basically this, which is R mod P. Okay, because P is a maximal ideal of R. So, you know, if you don't change anything. Okay, so therefore R dash mod M is basically or R mod P, where M is the unique maximal ideal of R dash. Okay, so this shows that this is a finitely generated K algebra because so is R. So R dash over M, R dash mod M is algebraic over K, and where you use the Hilbert-Snow tensors. You have already seen this in various forms in Professor Patil's lecture. So therefore, since K is algebraically closed, you get R dash over M is exactly equal to K. Thus, K is the coefficient field of R dash. Okay, so you have this. So basically what you have done here is that you just formally verified that you have your coefficient field. The R dash is the localization of the affine algebra, and your K remains to be the coefficient field. You're not changing anything. Okay, so therefore, since this is true, therefore we invoke this result, and we can say that the derivation module, okay, is isomorphic to this dual of M mod M square. Okay, and we also have dir K R dash K is isomorphic to R dash omega K, where omega is the module of Keller differentials. You remember that we have still not said that we are using the module of Keller differentials. I have just said M mod M square. Okay, and this was the result which we had stated as a corollary here. Okay, so therefore you have these two. Now let us see. Yeah. Okay, so you already know that this is finitely generated as an R dash module, and also we have this natural isomorphisms from, if you go to omega mod M omega over K to this, okay, you are changing the coefficients from K to R dash, and this is R dash. In fact, this also I'll just customarily put as E stroke T, but this is actually fairly obvious. Just let me still mention, because anything which I have just stated, yeah, okay. So where the second isomorphism arises from the property that MK is 0. So this is just you just have to verify that every time the natural map actually gives rise to a map, etc., etc. So let me just for the time being keep it as E stroke T. Now putting all the isomorphisms together, we get this. This is isomorphic to your. You remember this was there already. This was there. This was there. This you have proved recently, and therefore you have home K omega mod M omega over K is isomorphic to this. Okay. So note that the vector spaces appearing in these isomorphisms are finite dimensional over K, and because the dimensions of a finite dimensional vector space and its dual are the same, we get that this dimension is the same as this. Okay. And therefore, but what is this dimension? Therefore, you have mu of omega is mu of M, and that is embedding dimension of R dash. So now the first case, that if D is the dimension of the ring, and if you assume that omega is a free R dash module of rank D, so that means your mu omega is actually D, and hence your embedding dimension is actually equal to D, and therefore R dash is a regular local ring. So one part follows from these observations, that basically what you have done is you have associated, this is the This is the kind of the star observation through which you are able to say this, okay? And because these are the duals, right? Here you have this is the dual, okay? So, and then from this, you will be able to say that, yeah, sorry, this is K, this is over K, it's a mistake. Yeah, this is the dual of this vector space over K, this is the dual of this vector space over K, but both these are finite dimensional vector spaces and their dimension of their duals is the same as the dimension of the original vector space, and from that it follows. But you know what this is? This is going to give you mu m, and that is your embedding dimension by definition, and also you have mu omega. So if you know that omega is free with the required dimension, then you already have the regular local ring condition. Okay, so this is how you prove one part. Now the converse. So if you assume that R is, I'm sorry, not R, I mean our definition is R dash. So if you assume that this is a regular local ring, and then you are going to show that omega is free. Okay, okay. Yeah, so conversely, suppose that R dash is a regular local ring, then you know that D is going to be the embedding dimension, which is D is the dimension and D is the embedding dimension. So you write this exact sequence, okay, of R dash homomorphisms where F is a free R dash module of rank D, because you know the finitely generated condition is always there. Okay, so therefore you just define the map with a possible kernel. You want to show it's free, so you want to show n is 0. So that's what we want to do. Okay, so we want to show that n is 0. Now R dash is regular, so it is integral domain. Therefore, since R dash is R localized at P and P contains only one prime ideal, say Q of R, and so R dash is basically this. Do you see what does this mean? P contains is only one prime ideal because of the domain. Where is domain being used here? We are saying since this is regular local, assuming this is regular local, this is an integral domain, and here you have affine algebra localized at a maximal ideal. So we are saying that P contains only one prime ideal, say Q, and therefore your R dash has to be this. So where is domain being used here? Okay, let us just move on and we will have time to come back to. Okay, so now what you do is basically what is being said is that you can safely change that R to R mod Q. This is what the purpose is. So you are making it a domain now. Okay, a priori we just said that it's an affine algebra over a field of characteristic 0, etc., etc. So we have now made it even more spatial under the assumption that R is regular local, that this is in fact an integral domain. Okay, so you can replace R by this integral domain R, and you have this equality. Therefore, this is a field. So you have dimension of R is height of P, and that is dimension of R dash, and that is D. Now, if you take K to be the field of fractions of R dash, which is the same as the field of fractions of R, and if you take S to be R dash minus 0, then you have your K is this, and therefore, again, we are using that module of Keller differentials under the localization. So therefore, your S inverse omega is going to be just this, because your K is this, okay? And the above exact sequence changes to this of K vector spaces, and we apply the previous observation that S inverse omega over K is equal to this, and that is equal to the trans. I told you, right? I'm just going to use a few facts because otherwise this whole thing would take a lot of time. So this is going to be the transcendence degree because I have the this is coming as the field of fractions of the domain, and that is the dimension, and that is equal to this. Okay, so then it would follow that your dimension of this S inverse n, this has to be 0 from the exact sequence, and n is a submodule of a free R dash module. Okay, n was a submodule of F, and n is a submodule of a free R dash module, and every element of S, remember, this is your S. Okay, so every element of S is a non-zero divisor on n. So it follows that S inverse n equal to 0 should give you n equal to 0, and therefore it's a free module of rank D. So quite a few things to do. It's not straight away obvious, not at all, because you can see that we have used the structure of the module of Keller differentials under localization, and also we have, what is the most important thing that we have seen is this, that we have linked this K mod, this K M mod M square, and the dual of that is basically your derivative. So if you can, let me just point out a very important point, that here, see, when we were proving this, we used the derivation module to sort of factor through. Okay, so, and this was extremely important, that when we were proving the part that if you have regular local ring, then what happens? Okay, I'm sorry, if you have a free condition, then what happens, etc. So we've used the derivation module to factor through, and there what we used was basically, yeah, we used this, and also we used this. So this was the kind of pivot, and then we linked these two. This was the most important thing that we have done, and a bit of technicalities here. Anyway, so more details will be filled up as and when I just fill up the details here, because here we have used this. Let me show you once again here. We have used this, that this is the transcendence degree. So this of course requires a proof, but we have just skipped it for the time being. Okay, so yeah, so I'll not, I will now, I have to move quickly to something else. So I'll stop this, and maybe we can keep the discussion pending for the time being. Let me just move on to something different. Okay, so we intend to talk about some normality conditions now, starting with the very important fact that you have the unique factorization structure. So this is, let us prove that, and gradually we will move to the safe conditions, and we will end our discussion in this context. And finally, we will be talking about the Jacobian criteria. Okay. Okay, so this is what we want to prove basically, that a regular local ring is a unique factorization domain. Okay, so you have a Noetherian ring. Then first observation is this is a very important lemma, that if you have a non-zero ideal of R such that it's a projective and has finite free resolutions by finitely generated free R modules, then it is free of rank 1. Okay, so this linking is very interesting, that using this projective structure and the existence of finite free resolutions giving rise to a free rank 1 module. So let us go through the proof quickly, and then you will see that how we use this to prove this result. So if you take a prime ideal P of R such that this is non-zero, can we do that?
P from V of A, if I take, then this will be non-zero.
Okay, so you have a non-zero ideal here. So you can actually choose a prime ideal P such that this is non-zero. Then this is RP free. Well, you need to do this. Well, this is also, although I have put it as E stroke T, but I don't quite intend it to be. We will see. We will finally decide. I'll have a discussion with Joydeep and finalize that this is what you need to use for this. So if you have a finitely generated module over a Noetherian ring, then projective if and only if MP is free RP module. So as we say that it's locally free, you know, I mean, this is a kind of a standard result, but still we need to add it at some point of time, that this is what we have to use here to show that this is RP free, given that you have the projective condition. Okay. Okay, so what? So now comes another very important observation, which is going to be of use, that since this is a non-zero ideal, so this is RP free of rank 1. Can somebody tell me why? Why suddenly rank 1 has come? You have the freeness, that's free, but why should it be of rank 1? It's a non-zero ideal of RP.
If it is generated by more than one element, then it cannot be free. So rank should be 1.
Should be 1. Okay. Okay. So now, therefore, you have this, the direct summand, and you have the free R modules F and G, such that you can write this. So again, I have just put it here that if you have projective R module such that P has a finite free resolution, and is a finitely generated free R module, this is what is very, very important, such that this is finitely generated and free. Once again, a standard result, but still we have to make note of these things. So once you have this, with where F and G are finitely generated free R modules, so if you localize, then you have this, and therefore you have free all over. So rank of G over R is the same as this, and you have this is rank 1. So this is rank of FP over RP. So this is 1 plus rank of F. Now again, hence it follows that A is a free R module of rank 1. So if you, once again, why, how can you suddenly say that A should be free of rank 1? So basically, once again, this is also a standard result, that if you have a Noetherian ring and F is a finitely generated free R module, now if M is an R module such that M direct sum F is free of 1 plus rank F, then N should be free of rank 1. Okay. So these are some observations which we are using just for the want of time, but these will be all added in the bigger detail. So therefore, we have this situation that if you have a non-zero ideal and you don't need anything beyond a Noetherian ring, that's enough. So you have the projective condition and existence of a finite free resolution by finitely generated free R modules ensures that it's a free rank 1 module. Okay. Okay. So now we are in a situation to prove this theorem, that a regular local ring is a unique factorization domain. So regular local ring, Noetherian integral domain, we know because we have already proved that it's
Sir, like, do we need Noetherian condition in this E stroke T?
Noetherian condition. You mean in this one?
Yeah, because it will come from wage, taking wage, and
That's true. That's true. Yeah. You are saying whether you can drop this? Are you asking that?
yeah, yeah. I think Noetherian is not required. I'm not sure though.
Probably could. Yes, you are correct. Yeah, this is what you use is the wedge, and probably you could. I'll still verify and confirm. Because,
Okay, sure.
let us, for the time being, since we are safely taking everything to be Noetherian, so I just didn't want to make any exception. Yes, you are right actually. So you can here because your finitely generated condition is given, so you can probably drop Noetherian. You are right. Anyway, so here you have the domain, and so it is enough to prove that every prime ideal of height 1 is principal. You know that this is the condition for proving that it's UFD. So we prove this by induction on the dimension of the ring. Okay. Okay. So D is 0, then it is a field, and there is no prime ideal of height 1. So it's being vacuously satisfied. Now D is greater than or equal to 1, and P is a prime ideal of height 1. Okay, you assume. So we have D greater than or equal to 1, and let me now open it in the, okay. So we have D greater than or equal to 1 and M non-zero, which implies that M is not equal to M square, yeah, by Nakayama. So you choose an element, then this is a regular local ring, okay. This we have already seen a number of times, in fact, and therefore this is a prime ideal. I have put it under red color because this is going to be used again and again. Okay. Now, if T belongs to P, then here is your P is your RT, remember P was the height 1 prime that we have started with. Okay, that we have started with. So then we are done its principal. Now, if T is not in P, then you just take this multiplicatively closed set and take the localization with respect to that. Then P R dash is a prime ideal of R dash. Okay. And therefore, yeah, so we are we have this extension R dash, and now we are going to use our that previous lemma that what happens to if a non-zero ideal, if it is projective and it has a finite free resolution, then it's free of rank 1. That's what we are going to prove. That's what we are going to use. Okay. So the first step is, so this extended ideal, which is again a prime ideal of R dash, we claim that this is R dash projective. Okay. So it is enough to prove that this is locally free. That means if you localize with respect to prime ideals, P of R dash, then this is Rp dash free. So you know that this is what is very standard, that you just show that for every localization at prime ideals, it is free, and therefore you have the projective condition. So what we do now is the following. Yeah. Okay. So you start with a P in spec R dash, then P is P dash R dash for some P dash in spec R, and P dash intersection S is phi. S is this, remember. Oops. Yeah. So S is this, where T is not in P. Okay. Now you have T is in S and also in M, and P dash is not in M, therefore. Okay, because this intersection, therefore you have dimension has dropped, and this is regular local because R is regular local, and we have that PR P dash is PR P dash, and therefore you have the height condition. Induction hypothesis tells you that this is principal, hence this is RP dash free. Okay, so you are going in stages. That first you can understand, actually we are going to prove 3 such claims. That first you are showing that this extended ideal is projective over R dash, then you are going to show that it is principal, and finally you will show that this is principal. Okay, so you are going to the extended ring, and then you are coming back to P. Okay, so this settles that this is projective. Now, once you have the projective, you are going to prove now that this is principal. Okay, so P, please remember, this was your P. P was the height 1 prime that we have started with. P is the height 1 prime that we have started with, and we are trying to prove that it is principal, and we are using induction on the dimension of the ring. Okay. Okay, so now the projective dimension is less than or equal to the global dimension, but it's a regular local ring, so it's finite. Therefore, P has a finite projective resolution by finitely generated projective R modules. Okay, and then since R is local, each PI is free. Therefore, since R dash is R flat, R dash was just the localization with respect to S. So we have the finite free resolution here of the ideal PR dash, which is R dash projective, right? And therefore it should be free of rank 1 by that lemma. Okay, so you just showed that existence of finite free resolution. Okay, and the finite free resolution has come because of the finiteness of the projective dimension, which has come because of the finiteness of the global dimension, which has come because of the regular local. So just be aware that where exactly what you are using and what kind of conditions is coming into action. Yeah, so therefore you have, once you have, so you are, as I have said, that we are gradually moving. We just said, we just took it to the extension to PR dash. We showed that it is projective, then we settled that it is principal, and finally we are going to show that P is principal. Okay, so you have proved that this is principal, right? So therefore, PR dash is your, I'm sorry, I wanted to write X, S inverse. I mean, basically, no, what I wanted to write is that, so therefore I can write PR dash is XR dash, Now you have arteries here. Okay. So therefore, what it says is, since you have a non-zero ideal, etc., etc., so you can say that your X will belong here, but not here. It cannot sit in the intersection. So therefore, you can write X as y t to the power n with y in R, but y is not in RT. Okay. Now, since t is not in P, we get y is in P. It's a prime ideal. So therefore, you have this, that y r dash contained in p r dash is equal to x r dash, because of principle is contained in y r dash. So therefore, you have p r dash is equal to y r dash. Okay. And now we show that p is actually equal to yr. So that's what. So you have actually found a y in p. What have you done through this? What you have done is you have actually found a y in p such that p r dash is y r dash. Now you are saying that this is going to work in with respect to r also. Okay. So yr is contained in p is fine. Now to prove that this, you start with a z, then you write it like this, y a to the power a by t to the power n because of this. Okay. And then you get ya in this, but t is a prime element. Okay. If you remember, yeah, here T is a prime ideal. So T is a prime element and Y is not in Rt, so you get A in R to T to the power n, and therefore A by T to the power n is in R, and therefore Z is in YR. So quite involved, quite a few things, and gradually what you are doing is, so again, let me just show you the main thread, that what you have done is that you are using induction on the dimension. So once you have height 1 prime, you kind of, what you are doing is that you have situated yourself to a situation where you have extended the ring to this S inverse R. Okay, where S is this element, this multiplicatively closed set with respect to such an element T, such that T is avoiding P, but T is in M minus M square. Okay, so M minus M square, you can understand that this gives you the regular local condition immediately. Okay, so if you are working over that, then automatically you have a prime ideal here, and then through technical steps, you are gradually proving that this is a unique factorization domain. Very important theorem, and we have finally proved this. Yeah, so this normality conditions I don't want to get into today because this would take some time. But let me at least just tell you that what we will intend to do is that, I mean, I have not written the complete detail yet because it would take a little more time. But sort of, we are trying to show that that if you have, these are the conditions that we are going to talk about. That if you have, under what condition you have the situation that when you localize, then you have a normal domain. Okay. So how it connects to the regularity is what we intend to do, and we will be using these conditions. But let me not get into this today because it will be a sort of incomplete story. Okay, now I said that I would like to talk about that flatness thing. Yeah, if you remember, just to quickly recall, we were talking about flatness and fibers, and we were showing that conditions on an R and R dash and on the fiber ring, So how you can move from a condition on R to condition on R dash and vice versa. Okay, and I said that condition actually usually factors through conditions on the fiber ring, and mostly just with the flat condition. You don't need faithfully flat in most of the cases. That is what is interesting, because for faithfully flat extensions, we have already seen the flat descent, that there are certain properties which behave well. So here what we intend to show is that what are the properties which kind of safely carry over, but not always so automatically. It factors through the properties of the fiber ring. So we have mostly talked about what we wanted to. One more result which I would be talking about now. So quick recapitulation, you have this, that if you have local homomorphism of Noetherian local rings, This is how we define the fiber ring. Okay, the fiber ring of phi over m, and r dash is flat over r. Then you have this equality. If you recall that I had this kind of a purple statement there or here also, which eventually would be added in the greater detail. And then this you have seen, this theorem you have already seen, that you have this inequality of the height. Okay, and then if phi is flat, or more generally if the going down theorem holds, then the equality holds. This is something very, very important. And then we could use these things to prove this one first, that if you have r dash and f as above, and if r is regular local ring, r dash is Cohen-Macaulay, and if you have the dimension equality, then r dash is flat over r. So this was the first theorem that we have proved using the fiber condition. So here you see the fiber coming in this condition, okay, that to give the dimension equality. And the proof was by induction on the dimension. I don't want to go through the proof once again. And the technique was more or less the standard one, if you remember. See, choosing this element from here and then pushing on to this r bar and r dash bar and using the induction, so you can understand that you have to ensure that you have regular local ring and Cohen-Macaulay condition. And this is going to be used there. And finally, you bring in the Tor to settle the matter, okay, for the flatness. Okay, and then you remember that I said that this, again, I will not talk about now. So this is also one such thing. Also, although I have said is stroke t, but what I mean is that there are certain results which are just using in its face value. We are not proving, but I'll add the proof eventually. Okay, and then we use this. This is a very important observation, that if you have Noetherian local rings, local homomorphisms, finite modules, then you have this equality of the depth, in the sense that this depth of the tensor product is given by depth of m plus depth of this quotient module. Here also the idea was something similar, that you choose this maximal m sequences and then you put them side by side, and then you show that you get a maximal m tensor m sequence. Okay, and then you kind of yeah. So I mean, the techniques were similar. I don't want to get into the detail once again. If you just go through, you will remember easily. Okay, and then very important corollaries, that the depth equality, if you have a local homomorphism of Noetherian local rings, fiber ring is here. If you have flatness, then the depth is just straight away additive. And if you have Cohen-Macaulay, r dash is Cohen-Macaulay if and only if r and f are both Cohen-Macaulay. So here you see, probably for the first time, what I have said, that how properties of r and r dash, they behave mutually. And this is a classic example. You can see that r dash is Cohen-Macaulay implies r is Cohen-Macaulay. But when you are showing that r is Cohen-Macaulay, then you require the fiber ring is also Cohen-Macaulay to ensure that r dash is Cohen-Macaulay. Okay, and yeah. So now I am planning to talk about this one. Yeah, I think this is the, yeah, correct. So this is the one. This was pending. I just sort of kept it pending for a while. That if you have Noetherian local rings and local homomorphism, the fiber ring, let us assume for the time being that I have a faithfully flat extension, but then I will see if I can make it just a flat extension. Okay. So if r dash is regular, then so is r. And if r and f are both regular, then so is r dash. So it's kind of, you see, just now we have seen it for Cohen-Macaulay also, that r dash is Cohen-Macaulay if and only if r and f are both Cohen-Macaulay. And these kind of things were used, the depth equality, etc. So here, now we are having a similar statement for the regularity condition. Okay, but I have for the time being assumed faithfully flat. Let me mark this. Because my natural question would be whether we really require it to be faithfully flat. I've just kept it faithfully flat. Okay, so first part is that if you have regular condition here, then it is regular. But for going in this direction, you need the fiber ring to play a role. So we have the equality of this store, and the right hand side is 0 for I greater than dimension r dash. Okay. Yeah. And faithfully flat condition gives you this. Now this is where I am using faithfully flat. So the projective dimension is finite, but the projective dimension, assuming that R is regular local, the projective dimension of K over R is the global dimension, and that shows that your global dimension of R dash is also going to be finite, and therefore you have, just a minute. Yeah, fine. So yeah, so assuming that, I'm sorry, I wanted to say that R dash is regular. So you have, no, I think I have written it wrong. So you have, if once you have, this is finite. Now this I need to check once. Just anyway, let us skip this one for the time being. I think I need to add a few more details. So let me get into two. That if you have the regularity condition on R and F, then you have a regularity of R dash. So here what you do is, yeah. So assume that dimension of R is, so remember, we have regularity of R and the fiber ring. We are trying to prove that this is regular. So if you assume this is the dimension and this is the dimension of R and S respectively, now you just take this as system of parameters, follows from regularity, and then it maps to a regular system of parameters of, so this is a subset of N which maps to a regular system of parameters of F, that is all right. And then this generates N. Okay, so dimension of R dash is R plus S, and hence R dash is regular. So can we always say this? So I have regularity on R and F. So I have started with system of parameters of R, and then for F, okay. And I'm saying that I am taking that bigger list, and I want to claim that that has to generate N. And you have dimension of R dash is equal to R plus S, which shows that R dash is regular because you have the right number of elements. But can we just like this, can we just put them side by side, or we are using something? So basically what my question is that, so basically you see, I'm in a sense assuming that R is sitting inside R dash in some sense, right? So where are we really using faithfully flat? Because I'm still not in a situation to sort of loosen it to just flat. So my question is that where exactly, how exactly I can say that just take the system of parameters for R and the elements of N which is giving rise to a regular system of parameters for F, and then you just sort of, you can understand this is your F, right? This is your F. Okay. So you have these elements here. So the elements of n, which is giving rise to a system of parameters of this modulo m. Okay, and for m you are having this x1, x2, xr. Okay, and now I am just taking this bigger list, which, and I'm claiming that this generates n. Okay, and dimension of r dash, you know that we have all sorts of, we have regular local, we have dimension, and we have the, so all these we have already proved that. Just a minute. Yeah, so you have your dimension r dash equal to dimension r plus dimension f. Okay, so therefore you have the right number of elements in the maximal ideal. So my question would here be that, do I really require the faithfully flat condition, or can it be relaxed to, this is all right, that you can generate n using these right number of elements, etc., etc., and then regularity would follow. But where exactly your faithfully flat condition is being used, or can it be relaxed to just flatness? Okay, and just a quick comment that if r dash is regular, then r is regular by 1 above. However, f need not be regular. Now this example will come, that a small verification, I have not added it here, so that an example where you show that r dash is regularity of r dash ensures only regularity of r, but not of the fiber length. But for going from this direction to this direction, just regularity of r alone does not ensure regularity of r dash. Even if you have the all sorts of good things, you require the fiber ring also to be regular.